be a row echelon form, the nice ones, except for 37, which we already talked about. Number 8, no, yes, no, no. Number 8, A is no, B is yes, C and D are no-nos. Number 12, final solution is 2, negative 3, negative 2. 2, negative 3, negative 2. Number 22, final solution. It was a nice, easy one, huh? Negative 3, 2. Number 30 was inconsistent, no solution. I think we went over that one yesterday, right? Cool. Number 42, I think now we should be in 7.3b, which is homework 44, right? Oh, we're missing one? 30 is inconsistent, no solution. Because you get a false statement. Next, even. Number 42 was one of those ones where, what'd they give you? Oh, it's one of the ones where everything canceled out, 0 equals 0. So let z equal, nice. Solving, 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 you end up with the following expression. I'm slowly scrolling down. You can still see the solution up there. The final answer for number 50, when you plugged in your x's and your y's and got your 3 equations and then solved. You're not a computer, so you might have done it the faster way, but you should have gotten A is negative 1, B is 2, and C is 3, and plugged it in your nice little equation. If you graphed it, the points would have been on the parabola. Number 64, last one. Was this a word problem one?
No, the geometry one.
Oh, the geometry one, okay. That's why all the 180s, I should have figured that one out. The geometry one, they went ahead and stuck with the decimals. I think that's kind of gross. I would have gone fractions, but oh well. Final answer is Z is 94, X is 36, and Y is 50. As you were checking 64, in case something went wrong. Any evens or odds outstanding that we had questions on? Yeah, Ryan.
59.
59. Let me go look at it right now. Oh, he was a word problem, he won. Okay, anything else besides 59? Yeah. 42. 42? Okay, I have 59 ready. Let's go peek at 42. A couple more seconds, sorry. I meant to give you guys a little more time. Anything else besides 59 and 42? No? Okay. 42, let's go check him out. The system, if we had done our system, we would have taken the first two. Multiplied this guy by negative 2x, which would have been, this doesn't show all the steps, right? So it's kind of hard to figure out where your mistake might have come. So that would have been negative 4x minus 2y plus 6z equals negative 8. So that would have gotten you negative 2y plus 4z equals 2. So it's a negative? Oh no, it's a positive. Plus 8z. It's 8z equals 2. Oh, and that's the equation that's right there. And then they would have taken the bottom two equations and done something similar. This is what you should have gotten when taking the bottom two and probably multiplying this guy by just 2. Then you would have gotten the 4y minus 16z equals negative 4. Then we would have taken these two and tried to make them match by multiplying by 2. And that would have ended up canceling everything out. So you get 0 equals 0, and that's when we go to our let z equal a. And at that point, I mean, they kept going to row echelon form, meaning they divided everybody by a negative 2, divided everybody by 2 to get the nice 1 and then 1. Then they plugged in a and solved for y. And plugged in a and solved for x. Did you find it? Okay. And then number 59. Let me get out of this since we're done with him. Wastewater, what? It's a dirty problem. To make it cost and thousands of dollars for the company to remove P% of a chemical from its wastewater is given by the model. There we go. Oh, is this the wrong one? Oh, that's no fun. I mean, it is. I like partial fractions better than 7/3, but that's okay. Number 59. Thanks, guys. Oh, still, it's a Super Bowl problem. It was almost very timely. It's a little late.
What? 219? Super Bowl.
There we go. In Super Bowl I, ooh, Super Bowl I, the Green Bay Packers defeated the Kansas City Chiefs by a score of 35-10. The total points scored came from a combination of touchdowns, extra point kicks, and field goals worth 6 and 1 and 3, in case you didn't know. The number of touchdowns and extra point kicks were equal. There were 6 times as many touchdowns as field goals. Find the number of touchdowns, extra point kicks, and field goals scored. Now, some of you, just because of your knowledge of football, you just played with numbers until you figured it out. But others of you actually tried to make a system of equations. So, what do I know? I'm just going to go in order of what it is, right? X touchdowns, Y kicks, Z field goals. Is that cool? What equations did you guys get from the clues they gave you? If we're setting up equations, once again, some of you might have used your logic and just played around with it. But if we were actually using the clues, what do we know? The number of touchdowns and extra point kicks were equal. So X equals what? All right, that's one condition. What's something else? Nice mark. 6 times as many touchdowns as field goals. 6 times as many touchdowns as field goals. So I can say that the number of touchdowns, X, right? The number of touchdowns, X, equals 6 times field goals, which is Z. Hold on, some of you might have switched that one. There were 6 times as many touchdowns, so touchdowns were 6 times more than field goals. Does that make sense? That's why I say. What's the last one? Wait, what's the last one? We need 3 equations in order to get 3 unknowns.
You make it up.
No! You know the score!
35-10.
So how many points per touchdown?
35.
How many points per extra kick?
10. 1.
How many points per field goal?
3. Yes.
What's the overall score? And that's 4, but the overall points, 45. There we go. There are your systems of 3 equations. Because you knew that all of this had to add up to 45 points, and then you were able to use these clues. And technically, what would you guys have done?
Just look at it.
I would have solved for x first, right? Or not solved for x, but like gotten x, because you could have gotten that z is equal to x over 6, could have gotten that y is equal to x. You could have pretty quickly been like, oh, hey, look, let's just get it all in terms of x. And then z equals 3 times x over 6. Yeah, there we go.
This is a lot of math.
There you go. Solve for x, plug in your half y, plug in your z. Because you worked out z by itself.
You have they did. Oh.
Right? Then just solve for x. And then you're done. So we have 6 and we have 7 and we have 7.5. 7.5 is the same thing as what, 14 halves? No. 7.5 would be 15 halves. Then you would multiply by 2 over 15.
6.
Exactly. Which once again, some of you guys just played with the numbers. If x is equal to 6, what's y equal to? And what's z equal to if z is
36.
1/6? No, z is 1/6 of 6. You should be able to know whether or not you're right, because you could have been like, oh, hey, times 6, that's 36 points. Oh, hey, times 1, that's 42 points. Times 3, that's 45 points. Done.
They managed to make football popular.
complicated.
Those are really complicated.
But did he remind you of Super Bowl I and what happened? All right, cool kids. Here we go. Section 7.4.
How we do this season?
You run in China.
We're gonna buy the Chiefs or the Niners?
Yeah. Which one is it?
Both got no more shoulders.
Yes, I'm ready to go. And so should
National
you.
football.
Shush. Shush. I know, I should know better than to bring up football this much. Here we go. Here, I thought you'd be interested and you just got mad at it. All right, so partial fractions. Goal. You guys already wrote it down. To write a rational ratio expression. What's a ratio? Fraction. So to write a rational expression, a fractional expression as the sum of, so to write 1 as a sum of 2, I don't get it. To write 1 as a sum of 2, so we're trying to like break it down kind of, right? Taking 1, trying to get it written as 2. Now here's the point, guys. This is not a problem that needs partial fractions. This is a problem where the partial fractions have already been found. So this would have been your given. One big old rational expression, all put together, all simplified. I mean, it hasn't been factored, but we could factor it. Nothing cancels. That means the denominators are vertical asymptotes, not wholes. Wholes are the ones that cross out. Anyway. One big old rational expression, and guess who these guys are called? Partial fractions. Now, the page says equals. How could you guys test it to see if they truly are equal?
Combine the two fractions.
How do you combine two fractions that have different
X minus
denominators?
3 to the other side, and then X plus 2.
You could multiply x minus 3 and x plus 2 to the other side. I was thinking more of the old-fashioned common denominator thing.
I know what that is.
How would we get a common denominator if they don't match? Okay, so this guy gets multiplied by x minus 3, right? I'm not saying Andrew's way was wrong. I'm saying I was thinking the more old-fashioned way of common denominators. So, multiply, no, but you said multiply to the other side.
I meant like that. So you said like the other little fraction.
Oh, the other.
Yeah.
Got it.
I got 4 green.
Well, actually, the idea of the other side is going to be important for partial fractions. Maybe that's why I interpreted it that way. What happens when we multiply 2 times x plus 2?
2 plus 4.
What happens when we multiply negative 1 by x plus 3?
Negative X plus 3.
And denominator, don't I get x plus 2 times x minus 3?
Then you foil it.
And if I FOIL that, I get x squared minus x minus 6. Oh, hey. So these little guys were the factors of the denominator? And what ends up happening on top?
X plus 7.
Way to go.
So what's the idea of partial fractions? Taking a simplified rational expression and saying, where did you come from? What 2 pieces would you have? What 2 or 3 or 4 partial fractions would have been put together to make it? Does that make sense? So we're taking a big old fraction that has a common denominator already in it and saying, hey, you came from, or you could have come from, somewhere. So what would that have been? Now, there are some cool tricks with partial fractions that are going to be kind of nice, but there's also like a systematic approach that's going to work no matter what. That's what this big old huge paragraph step 1, 2, 3, 4 thing is about. This is the system. Not to say there aren't some cool tricks about partial fractions, but this is a system that's going to be super, super helpful. But hold on, we have a TA in the back that will help us for a second. Eileen, do partial fractions ever come in handy in calculus?
Yes.
Do they make impossible problems possible?
Yes, they do.
And she's specifically referring to what kinds of problems?
Integrals.
Mm-hmm. If you don't know how to do a partial fraction, there's going to be an integral one day that you won't be able to solve. Maybe not one day, because you might not take calculus. But if you do, the partial fractions are useful, at least in that context, if not in others. That's A, B, and B, C kind of. So we're going to talk about them. And we're going to learn how to do the math behind what makes an impossible problem possible for kids in higher math.
Yay.
So here we go, partial fractions. Number one. Ooh, AB talked about this today. Nice. They haven't done a partial fraction yet, but they did talk about this. If you see an improper rational expression, the very first step to simplifying it, to breaking it down into its simpler pieces, is to divide. Just like you would do if I was to say, hey, how could you make 37/5 simpler? Yeah, divide it and say, well, 5 goes into 37 7 times and 2/5. Couldn't you explain to a little elementary kid 37/5? Oh, it's so much easier if you think about it like, right? Okay. Kind of the same thing here, except it doesn't look quite so easy to you in the sense of, oh yeah, it does, just make a mixed number and that makes more sense. We're trying to break down someone that's harder or more complicated into simpler pieces. So the idea is, a fraction, a rational expression, will be improper when the degree of the top, the numerator, is higher than the degree of the denominator. Whenever the degree of the numerator is higher than the degree of the denominator, we divide, aka polynomial division, aka long division. Why not synthetic? Because it only sometimes works. Okay, after you divide, now, if it's not improper, you don't divide. Go to step 2. If it is improper, you divide first, then go to number 2 with the remaining fraction. If you divide, you're now only breaking up the remaining fraction. You already know the beginning. Okay, number 2. Factor the denominator. Why? Look at the example that we just looked at. This is like an entire solution, beginning and end, given, and then partials. We haven't seen the in-between. But do you see how the partials had the factors of the beginning? That's why we have to say, oh, hey, who are the factors of the denominator? They're going to help us form our partials. Totally factor until you cannot go any further. Sometimes you can't go any further with a quadratic because its factors would be imaginary. We're only staying real. We're not going imaginary, okay? So, factor until you can't go any further. Sometimes you'll be stuck with a quadratic. Usually you'll have the nice little linear like x plus 2 or 2x minus 1. Usually you'll have linear. Every now and then you might have a quadratic that can't be factored anymore. Number 3 says, take all those factors, whatever you've got, actually 3 and 4. It says, take all those factors and form what your partial fractions need to look like. Form partial fraction decomposition. Ooh, we decomposed stuff, haven't we, guys? Do you remember where we decomposed before?
For logarithmic things.
Logarithmic, we expanded and condensed. It's kind of the same idea, super similar, but we actually used decompose. What were we doing?
That was
We were given something that had been put together, and we were trying to take it apart to say what its pieces were. Had something to do with F of G of H of what? What is that though? What are those? Compositions. Compositions of functions. Remember we were given something super, super nasty, like the square root of 1 plus sine squared of 1 over 3x plus 2. Although you probably didn't have a sine squared back then, so I was trying to be nice to you and haven't done a lot of trivia. But then we were supposed to look at this guy and say, hey, who's the innermost? Remember this? Who would the innermost be? Okay, I wouldn't be too mad if you chose that. I would probably choose this. But yeah, this is the innermost. Then who's the next guy? That would be our H.
That was G.
Well, F of G of H, innermost.
Oh.
Because we're gonna need a few of them. Who's outside of that guy?
Sine.
Yeah, we could say sine, that could be g. F could be 1 plus x squared, and then sine got plugged in. But then we would need another letter like b or something to be the square root. Anyway, we could have 1 there, we could have 1 here with the sine being squared, we could have 1 here under the square root. Okay, we did decompositions back then. But now, we're not taking a big old nasty composition and saying, hey, where did you come from? We're taking a big old nasty fraction and saying, oh, what were your pieces before the common denominator was found? Real quick, if it's a linear factor, you need to just put a constant up on top, and I'm going to technically probably put like a and b, dot, 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 c, d. They just use a's so we can use the same letter, and they don't have to like stop it. They can show you what's going on down there. I'll probably just use a's and b's and c's. And then whatever letter I don't use in those, I'll use down here. So that could be a cx plus d, it could be fx plus g, I don't know. But if you were to have a quadratic that's irreducible, that could not be factored anymore, you wouldn't just put a constant on top, you'd put a linear equation on top. But the whole point is, guys, once we factor and once we make these little fractions, we don't know who these constants are. We have to find them. And in the example on the page before, they didn't tell you how they got to, I didn't tell you how they got to, 2 and negative 1. It just kind of magically was there, and we said, hey, I wonder if it works. And did it work? Yes, but the problem is, even after we factor this guy and get these two factors, where do these numbers come from? Well, that's what we're going to have to figure out. That's what we're going to have to figure out. So the whole big old table was basically saying, partial fractions, here's who they are, here's how you start solving for them. Here's who they are, and here's how you start solving for them. But that table ends at us having them all written out and ready, but no answers yet. I hit a button. Oops. So then this page says, okay, let's pick up where we left off. We have these partial fractions with unknown numerators. How on earth do we find the denominators? Nope, wrong way. Unknown numerators. How do we solve for the unknowns? I just thought it was Saturday. It was going to get really hot in here. Most of you won't read that huge, huge, huge table on the page before. So this is our quick summary, along with our what do we do next, which is somehow missing. Let me add in a step 5 real quick. Okay. So for number 1, if the fraction is improper, after you divide, keep the polynomial, take the remainder, and form partial fractions of the remainder, who's a fraction. Number 2, factor the denominator completely as much as you can for linear factors. Any sort of mx plus b that you might have. Just put a constant up top for quadratic factors. Any ax squared plus bx plus c. Make sure you put a linear factor up top. And then once you have this whole shebang, let me show you what I mean. Once you have this whole n of x, the original numerator, over d of x, the original denominator, equal to whatever partial fractions you might have, and I'll just go ahead and make, I don't know, 2, we'll do that m1, b1, m2, b2, and then we'll say maybe there's a quadratic one too. This is a nasty problem. M3? Nope, this is a quadratic. Ax squared plus bx plus c. What I want you to do in order to solve, we're not talking about the tricks right now, we're talking about the systematic way of approaching it. To solve is you multiply both sides of the equation, the original and the partials that you've found, but you still don't know what goes up top in them, by the original denominator. So multiply this side by d of x, and what's going to happen when I multiply this side by d of x? You're just going to cancel, I'm just going to get the numerator. And then multiply this side by d of x. This is where it's going to get interesting. When I multiply by d of x, question, where did these little denominators come from? Do you remember where they came from to begin with? Look at step number 2. Where did each of the denominators come from? From the factors. Which means that when I go to multiply d by this guy, is this guy going to be in that denominator? Yeah. And he's going to cancel and something's going to be left. When I go to distribute here, that guy's going to be in the denominator. He's going to cancel. You're going to put whatever's left. And then when I come into this guy, he's going to be in the denominator also. He's going to cancel. And we're going to have whoever's left. Now I could keep writing the notation of this. It's going to get really messy really fast. Because for instance, I could say that a is going to be left multiplied. When I take this away from the denominator, he's going to be multiplied by these two guys. B, when this gets brought in, when that cancels, B is going to get multiplied by those two guys. And then Cx plus D, when that guy cancels, is going to get multiplied by those two guys. And what's weird is we have one big, huge equation. No denominators, but one huge equation. And I say simplify and solve the remaining. What? I thought systems have to have multiple equations. We're just going to have one. Let's go try one. Ooh, it's the one that we were given. Let's go figure out how they got the, was it 2 and -1, or was it -2 and 1? Anyway.
Negative 2. Oh, wait, 2 a negative 1.
3 negative 1?
Two
Wow.
negative 1.
2 negative 1. Anyway, let's go figure out how they got their numbers on top. I want you guys to go ahead and start the steps. And the first step says, divide when improper. Applicable or not applicable? Not applicable, because the bottom's degree is 2 and the top's degree is 1. This is not improper. The bottom's degree is stronger. There's no reason to divide. So, what is there a reason to do? Factor. All right. Let's not rewrite that guy that way. Let's rewrite that guy with his factored denominator. And his factored denominator would be x minus 3 plus 2. Sorry, x minus 3 times x plus 2. As soon as we factor the denominator, then we go ahead and say, oh, hey, there's going to be 2 partial fractions. You can cut this fraction into 2 pieces. There are only 2 denominators. So it could have only come from a fraction with an x minus 3 as a denominator, or a fraction, I should say, and a fraction, with an x plus 2 denominator. Now, since these both are linear, as indicated by the degree, no quadratics down here, I'm going to put an a up top and a b up top. This is what our steps get us up to, up through step 4. Now, what does step 5 say to you? multiply both sides of the equation by the denominator, the original denominator, aka the whole denominator. Which means I'm going to multiply both sides by x minus 3 times the x plus 2. What I do on one side, I have to do on the other. And if you want, if it's easier for you, you could just do one big ol' x minus 3 times 1x plus 2. But a lot of kids kind of get confused with that because they forget that both of them need to distribute to both of the insides. So if you want, you could technically write it for every single term. I'm going to do that just to be very, very, very clear as to what I'm doing. Now guys, go ahead and simplify, because a lot of stuff simplifies, right? Okay, go simplify. Yes, this homework is not due until Tuesday, meaning you should definitely start it this weekend. But what else am I giving you that you can work on this weekend? Any of the other tests? I want you guys to write what you have left. And I think what you have left should look like A being multiplied by the other guy's denominator, B being multiplied by the first guy's denominator. And my question to you is, how on earth could this be a system? And the answer is, there are x terms and there are constants. There are x terms and there are constants. Now there are cool tricks where we could plug in x is -2 to everybody, or x is 3 to everybody, and we'll see some of those tricks on Monday, hence why you don't want to do this entire homework this weekend, because there are tricks that make things faster. But long story short, if I take all of my x terms, I have one x from the left, and on the right, I would get x terms of ax plus bx. And if I divide everybody by x, I get 1 equals a plus b. And constants, from the left side I get 7, and from the right side I get 2a that has no x, and -3b that has no x either. And all of a sudden I have a system of equations. When I call your name, come up and grab your test. Caro, David, no, Ryan. If you have a .5, it'll get rounded up when it gets to the grade point. Rebecca. Thomas. Andrew. Ryan, Hicks. Jack. Joseph. If you have your test, you name me. Colby. Caroline. Dean. Kevin. Victor. John. Melanie. Colby.
Thomas, are you going to take
And Bye, guys.